Hey everyone, my name is Henrik. I am a PhD student at the moment at Erasmus University Medical Center, and we recently published an article in the International Journal of Medical Informatics titled Logistic Regression Models for Patient Prediction based on massive observational data. And basically the question that we're asking is, do we need all of the data that we currently have available in our databases? And well, this is a prediction study. We're using primarily Odyssey tools, in particular the patient prediction framework. And I'm going to start with some background if this moves. So in machine learning, you have this, or there exists this notion that more data is generally better. And that is because in general, models that you develop on more data will, or at least tend to generalize better to your validation data or to your holdout data set. However, what we now have in Odyssey is that we have such massive amounts of observational data available that we were actually asking ourselves, do we even need all of this data? Because you can imagine that using less data would result in, first of all, much smaller demand for computing resources. Then second of all, much shorter model development times. So just the process of fitting would be much quicker. And third of all, we also, or it would at least facilitate much larger scale prediction analyses. For example, similar to what Legend did, we could predict within hundreds of different target populations, hundreds of different outcomes, and do this also across multiple databases. So this is the idea. And to study that, we decided to generate learning curves for 81 previously defined prediction problems. And we also did this across 3 US claims databases, and those include CCAE, MDCD, and MDCR. And basically, what you would do to generate a learning curve is, for each of these prediction problems, we developed a set of prediction models on an increasingly larger subset of this full training data set. And then we simply recorded the discrimination performance of each of these models. And that basically gave us these data points for each of the learning curves. So you can imagine these are 81 times 3 learning curves. And then we also fitted these with the power law function to smooth them out a bit, which then also enabled us to apply a threshold criterion. And that's actually a really simple criterion. So all we're doing is we're looking at our full model. So this uses the full training data set. And we're basically subtracting a little delta, which we call the threshold. In this case, I have an example here of a delta of 0.02 points AUC. And then we look when does this new performance is achieved on the learning curve. And the way you can read this is basically, if you're willing to sacrifice 0.02 points AUC, you might be able to reduce your sample size. And very importantly now, the sample size we are measuring in the number of events rather than the absolute number of samples. But in any case, you would be able to reduce the sample size from around 4,000 to around 1,600. And this is then what we would call the adequate model. And we basically did this for all the prediction problems across all the databases, and that gives you this. So on the x-axis, again, you have the number of events at max AUROC performance, and this basically just corresponds to this number of events of the full model. And then on the y-axis, you have the number of events at the threshold, which again just corresponds to the adequate model. And then we assess for 4 different thresholds between 0.001 and 0.02 what the possible reduction in sample size is. And again, I can just give an example. For example, from here on the bottom left, let's say you are willing to sacrifice 0.01 points AUC, then you might be able to achieve a reduction of your sample size from around 15,000 events to about 5,000 events. And this is, of course, in absolute numbers. And then we also computed the relative reductions or percentage, and that basically shows us that for a model developed on 15,000 events, you can expect a reduction, let's say a mean reduction of around 70%. So there's certainly some spread here, and also depends a bit on the actual number of events available to this model. So this is the first thing we saw, that basically, if you're willing to accept a small decrease in performance of your model, you can actually reduce your sample size quite significantly. Another thing we were interested in was the number of predictors. And well, this is an interesting one because we are, in this case, only looking at logistic regression models. And for our logistic regression models, you could approximate the model complexity based on the number of predictors in your model. And what we, for example, do in our Odyssey prediction, well, in our studies, is whenever we publish a paper, we first of all, of course, disseminate the full model, but we also always try to share a parsimonious model with a reduced number of predictors, simply because it's easier to apply in clinical practice, and it's probably also will have more uptake. And we observed something very interesting as well here with the learning curves, that when you reduce the sample size and you develop your models using Cyclops, in this case, logistic regression models that are L1 regularized, you will also see a reduction in the number of predictors in those models. For example, again, for a threshold of 0.01, we observed, for example, for a model that initially had 1,000 predictors, this was reduced to about 500. And again, we could, based on that, compute the relative reduction. So this gave us roughly a mean reduction of about 50%, even though in this case, of course, the spread was significantly larger. And then, yeah, the conclusion is that considerable reduction in sample size and model complexity was possible, and that was then in combination with a rather small loss in performance in terms of AUC. I have the paper link here, so please check that out. I think we have a lot of cool intuitions in there about developing specifically logistic regression models on observational data. And well, since this is an empirical study, there are also quite a bunch of limitations that I didn't cover now, but that are mentioned also in the paper.